Good morning. This is Barb with D3 Technology, and welcome to Inventor Design for 3D Printing, Additive Manufacturing. And this morning we have Kevin Marchant, who is 3D printing technical, and of course I am on the sales side of D3 Technologies. D3 Technologies is basically involved with helping manufacturing companies be more successful. We do that through a variety of areas, whether it's through the Autodesk product solutions, or through our CAM solutions, or through the 3D print solutions that we offer. By the way, we do offer 3 different varieties. We offer 3D Systems, they're our partner. We also partner with Markforged, and we partner with 3DP Platform. So obviously our whole goal is to work with you to help you out in a consultative role to help you become even more lean in your processes and technologies. So here's what we're going to cover today. We're actually going to, I'm just going to do a quick overview of additive manufacturing operations for 3D printers, but I'm also going to let Kevin then take the last 3 bullets. Kevin's going to focus on optimizing Inventor design for specifically 3D printing. He's going to take you through how to kind of use the STL settings and get things set up that make sense. And then of course, various design considerations whenever you're actually 3D printing, because that really does come into play for your parts and assemblies. In terms of 3D printer technologies, and I'm sure most of you guys know a lot of these are the majority of what you find in the US today. There's either fused deposition modeling, or it's called FFF, fused filament. That's one application. As you know, that's really used, a technology that you see a lot with the tabletop printers, but it is a process by which you use a filament that's injected through, and certainly it does produce nice models. Then you've got color jet printing technology, or CJP. That technology actually uses basically a gypsum powder along with a binder and inkjet cartridges to help provide colorful models, more used a lot in education, used a lot for concept parts, as well as architectural firms. MJP, or multi-jet printing, is actually a technology. It's much like inkjet printing, but it uses jets of acrylate plastic or plastic materials of some sort, and uses UV rays for curing. It really provides great technology for detailed parts, as well as strength parts. SLA, which everybody is probably familiar with, stereolithography, of course, uses a resin type material for producing, using laser for producing really the gold standard in terms of 3D printing. It doesn't get any better than SLA. SLS, selective laser sintering, uses a nylon powders, various types of nylons, whether it's high temp, high strength, whatever it might be. And then again, a sintering process for a high laser to sinter the material. Last but not least is DMLP. That's direct metal laser printing. Of course, that's where you're getting into your metal printing. Again, it uses a laser, selective laser sintering process, but you're using powder, of course, right? Metal powder, along with a high-powered laser. So that kind of gives you a quick overview, and now what I'd like to do is turn this over to Kevin Marchant. As I said, Kevin Marchant is actually the individual that deals more on the technical side. So Kevin, I'm going to let you have it.
Great, thanks Barb for that introduction. So again, as Barb said, I am the technical side. I work on the printers as well as with D3 Technologies. I train on the software as well. So kind of hands in both hats over there. So one of the things we're going to talk about today is when we design parts to be manufactured, we have to look at how they're going to be manufactured. In this case specifically, we're looking at parts that are going to be manufactured in rapid prototyping, 3D printing, and depending on what technology of 3D printing also will benefit us from varying degrees and varying methods of design. So the process that we're going to talk about first is the most common that we see out in the world, the one that if you talk to somebody and you say, hey, you know, I've got a 3D printer, they're going to assume you have an FDM or an FFF type printer. You know, think of weed whacker line that gets melted into a smaller diameter and then built on top of other plastic itself, and then voila, you have a shape. And so I've got a few examples that we're going to look at with that, all of which apply to, again, the CJP that Barb talked about, or the multi-jet technology that just gives us a finer resolution. We'll talk a little bit about that here shortly. So first, we're going to look at kind of the differences of how we manufacture things that we know are going to be printed versus the things that we know are going to be machined or otherwise manufactured. You know, I'm going to really avoid kind of the topic of sheet metal just because it has its own environment altogether. But if I was going to machine a simple box, so if we look at this guy right here, if you notice it's a cracker box, I designed it for hauling and keeping crackers safe on runs. And so knowing that I could print this much cheaper than I could have it manufactured, things that we want to look at is wall thicknesses, corners, and joints are usually the big things, especially when we're talking about any kind of assemblies that are out there. Pardon me. So the joints that we created in here, very simple beveled joint, allows it to be clamped down, held together with a rubber band, or even just by force of being together, keeps those two halves from sliding apart. And you'll notice it's a large surface area across there. If I actually come in here and measure this guy, you know, I've got a distance of almost 1/4 of an inch of surface across there. And that's just due to the fact that when we print with an FDM or FFF technology, then this is coming in here in layers. And so the layers across here, I want as much contact as I can to give as much strength as I can as well. And when we're talking about strength, if I look at just the wall thickness of this guy in here, if I pick the right two faces the first time, you know, I've got an 1/8 of an inch wall. If this was going to be machined out of aluminum or something, I could easily go 1/16, or even if it was going to be a steel, I could probably even go thinner than that, being that the most pressure exerted on this box would be, you know, less than 200 pounds in here as it rolls around in a backpack on a race course. So again, you know, we're looking at almost doubling the wall thickness in this case for the strength of this box out here. When I printed this, I was able to stand on it. My wife runs with it. I can put 230 odd pounds on it, no issues, no cracking, the whole 9 yards. So it was substantial in its strength in the printed form. Again, if I was going to machine that, the other thing that I would do is I would change this. This, you know, that would end up being a very, very sharp edge that I would not want on a machine. I'd go to a corner lap, similar to a snap together box or something that would allow the same type of side-to-side resistance, but much smaller due to the strength of the metal versus the strength of the polymer plastic or whichever filament I was using in the printer at that time. So that's one thing we want to keep in mind is just that the geometry, we don't want it to be anything super complicated. You know, I could have put individual compartments for crackers or whatever that I want to carry in there. But with the printing, it's going to be faster for one if I keep it a little bit more basic. And that's what I was looking for here, was just to be efficient with both the material and the time in there for that guy. And whereas machining, we can get a little bit more elaborate, but we've got the strength there to support that elaborateness or elaborativity, if I can make up a word on the fly, in there. And so when we print, the other thing we can do is also look at our corners. You know, that's one thing that the printers are really good at portraying out here is these nice filleted corners. If we have a hard, sharp corner on the outside, they can tend to be just not as appealing, and we'll see that in a photo I've got of a later model. A little bit out here, you can see kind of the sharp edges aren't as sharp as what we'd like them to be. So we tend to round a lot of corners, just mainly for aesthetics, not so much as strengths out there on that guy. So again, wall thicknesses are huge. Probably the biggest thing we think of. A lot of FDM or FFF technology, you'll see nozzle size or print resolution referred to as the diameter of the nozzle. For instance, we can print 0.1 all the way up to 0.2 on some of our printers, and even some of the other printers we deal with get up into very large nozzles for rapid printing at a low resolution. Again, just depending on what it is you're looking for, whether you're looking for aesthetics, strength, speed, quality, all those things fall into there. And so we can design with that knowledge of our resolution, because I know if I've got a smaller resolution, A, I'm going to pick up this corner better, and B, I'm going to be able to get a further point on my contact surface out here. So resolution is one thing that you want to pay attention to, want to be aware of while you're printing and while you're designing. I couldn't print this on our largest nozzle that we can run on our biggest printer, that's FDM, just because it has too much detail even with a simple box. It'd be really fast, but the detail would not be there. Even though this may look like a simple box, detail does matter in that regard. Talking about detail, so I came up with a part. We're going to shift gears just a little bit. This is a very small piece. I don't have a picture of it handy on my computer, but we can look over here, and this goes all the way from a 0.005 space all the way around this little axle shaped piece here. If we go up here to our view and we do a little half view, you guys can see what this shape actually looks like. That'll work too. Let me pick a different face to run that off of. There we go. So we can see we came in and created these little H shapes in here for the purpose of printing on, in this case, was a multi-jet printer. It's a 2500 that we have here in my office. And what this allowed me to do was, once I post-process this part, then I could see how loose this piece fit with a clearance of 0.02 inches, all the way down to a 0.005 tight fit here. And so it allows me to judge if I need to print an assembly, because the way that CJP works, using a wax support system, we then melt that support system out, which frees up this geometry in there. And so even though our assembly may have this much space or that much space in it, we have to know the technology we're going to use to be able to print that and actually have those parts movable in reality. And part of that revolves around the technology we're using. CJP, again, we have the wax, or sorry, CJP uses a powder in there, as Barb alluded to. And so that gypsum-like powder is, when it is unbound by the binding liquid, then that becomes a support material. And so we take that part out and basically give it the equivalent of a little shake. We can use vacuums and a little bit of air pressure to blow that dust out of there, that powder out of those joints, and then move them. And so we can see what kind of clearance we can get out of those parts. If you're unfamiliar with that technology, it's very common to see a ball bearing as the ideal print, because then it shows how we can make movable, but there's always a little bit of slop in there, and that becomes kind of the question is how close can I get? Well, we can get as close as those granulars are out there in space, you know, when we're laying those layers down. And so with the tolerance in mind also comes detail. And so the other advantage of this part, when I come out here and come out of that, is I can see how much visually how much gap is in there. So then I know when I create text or a label or anything like that with my print, then I know how thick those need to be. A, to be visible. B, to be able to clean that wax or support material out of, so then that feature is visible. And so that translates over into any kind of recesses. If we need to make a pocket to apply a label on our print to look like the real product, all those kind of tolerances in there all really help figure that out. So sometimes we may want to create just a part that we can print so we have a reference to go back to. And then in this part would not function well for FDM or FFF technology, just due to the fact that it would be hard to remove the support structure in there. And or come in here, we can get with these larger, depending on the diameter of our bead or our filament combination that we've got out there, we can see some of that detail, or we may not see that detail. Again, if I've got a large diameter in my world, if I've got a large diameter, I may not even see that 0.02 thickness here, versus if I'm running a smaller head that's going to take me longer to print, but give me a higher resolution, I may even be able to see all the way down, to that 0.01 out there and see the difference in there, the lack of material there. And last topic, next to last topic actually, is we're going to talk about, so another part that I created, basically a tool to clean up my desk, my personal desk in my office. In my world, we use USB drives a lot, from loading software to copying files. Even in printing, we can offload our STL file to a USB drive, take it over to the physical printer, plug it in, and print from that. If for whatever reason isn't on the network or is in a location that's unable to be on the network. So I use a lot of USB drives, a lot of pens, and I get tired of them laying on my desk. So I threw a print together. Large block was a simple design. If I timed it, I probably had 20 minutes laying this guy out, with a quick ruler and to get the USB plug sizes and a couple of different pen sizes and whatnot in there. And I printed that guy off. And what I learned from that, this was kind of in my earlier days of FDM printing, was this large block. And this is a 4x2 roughly block that's about an inch tall, maybe 3/4. But anyways, that large of a material on that small of a footbed, this guy warped. So that whole block, if I hold down one side, the other side's a good 1/8 of an inch off of my desk. And so as soon as it printed and I noticed how badly it was warped, I realized I needed to redesign this part. And so I thought to myself, how can I get the same number of items in here to, again, clean up my surface out here, but have a successful print? Well, so what I decided on was an arc. So fans everything out. This particular radius that I used in here, if we look at this guy, we can see it follows. That arc was at such an arc that I did not need to print with support material, which in this case was beneficial because this printer support material wasn't always the easiest to remove, and that's something that we have to deal with and something we want to pay attention to, again, using that FDM technology or FFF technology. If we don't have dual heads and if we don't have the ability to use rinse away support material, that kind of stuff, we have to physically break it out of there. And so when I created this shape that didn't have anywhere near the surface volume, but performed the same function, held 6 of my USB drives and 5 of my pens, printed that guy out, and he is perfectly flat. There, I can push on any corner of him, and there's, if it raises, it's raising by maybe a 64th of an inch, which is perfectly acceptable for a desk organizing tool per se. And so this can apply to many things out there. You may not be able to go from a rectangular cube to or a rectangular block, I should say, not a cube, to a arched piece. But sometimes if you have that freedom, then things like surface area, we can decrease the surface area by opening it up. And that's going to allow the heat transfer and everything to be much more efficient. And therefore, when the plastic cools, it's not going to peel up and peel away. The other advantage to this is I did all this from design 1 to design 2, which included redesigning my USB shapes because they didn't fit the first time around. My tolerances were too tight. And I think I had 1 or 2 that fit all the holes, but I had a couple others that were a little bit bigger, didn't fit and whatnot. So in the wonderful world of standardization, I just made everything a little bit bigger out there. And so with that in mind, I printed that out, and it works. It works great. We can see, here's a picture of kind of so we can see here's my first iteration, the second iteration here where it didn't warp. Figured out that, I think on this one you can see where I tried cutting to see if it was just a top layer issue, keeping my USB drives from going in there. And then on the final one done at a higher resolution, opened up, I've got a organizer that works great on my desk for that. And later printed out with a different technology, so it's even cleaner. Now I just don't have a picture of that one, but it's the one I actually use. So with a little bit of design thought between temperature control, overall material use, layer detail, those are all very important to especially that FDM, FFF technology. Our CJPs, they have a much tighter control over the layers. The huge advantage there is the reusability of the support because it's the same as the print material, just unbound. And we can throw graphics on those as well, give it color if we have a color-enabled printer. So that's a huge advantage of the CJP technology. And then the multi-jet is relatively open-ended as far as geometry goes. The area you want to really be careful with those is wall thickness. If you do get it too thin, it's going to be fragile. We do have to melt the wax away when it is hot. Then if the walls are thin, they can be pliable, sustainable to warpage, or even physically bending those in while you're just trying to maneuver the part. When we remove the support material away from it, and then just really opens up our boundaries. So once we're done with these, then what? Then we've got to push this out to an STL file. That is one of the main tools that we use for printing files, kind of an industry standard out there. And so with Inventor, at least, and that's what D3 deals with, we deal with the Autodesk manufacturing products out there. We have a very simple print, send a 3D print service, which is going to export us out to that STL. I can also get to the same menu if I come out here and I say export to a CAD format, and then I can pick STL, but I got to go through and pick other options. And to me, it's just easier. If I go to my print, it takes me straight to STLs. The biggest snafu that especially newer users get into, or that environment where you're accepting STLs for somebody else within the organization or whatever, when we're dealing with STLs, is the scale. Did they design this part in imperial units, or did they design it in metric units? And so we want to pay attention to the scale here. If we're familiar with the part, like I said, I know this guy is about 2 by 4 by a little over an inch height, so I know that's right. If we get the part from somebody else, then we want to make sure and check, have them send the dimensions, the overall, even just a couple of them, so you can verify that. Or else you get what's supposed to be a big part as a teeny tiny part. And I have examples of those on my desk. Good lessons to be learned. When we come in here, again, we can either pull source units, which is what I like to do, because then it doesn't matter what I model this in metric or inch, it's going to carry those over. Our resolution, I always leave it on high. It's just going to give me the most triangles that I can get out there in my STL. It's going to give me my best resolution print in there. If I have really complicated geometry, I may come in here and tweak these guys. These are the default settings, 41 and 0. And all that's going to do is going to give me either a little tighter tolerance or a little looser tolerance as far as the geometry translation from my native file to the STL file. I have yet to have to tweak those to get a good STL out into my software. Max edge length, we want to put that 100%. We don't want it chopping any edges off, any ratios. We don't, just all those guys. Those defaults are usually right on the money of what we need. STL has been around since whenever Chuck Hall created it back in the mid 80s, early 80s. Barb would know that date better than I. But so pretty simple. Binary works. Export colors is really irrelevant to our world because, again, the color is going to depend on the technology. Again, if I've got CJPs in the software I use to print from, we can apply colors to that or images to that. In the MJP or the multi-jets, then it all depends on what material is loaded. If I've got a clear material loaded, if I've got a white material loaded, if I've got a black material loaded, it's just going to be those. There is no color options with those. In there, with some technologies, we can mix durometers of materials and we can get different shades between, for example, black and white. In there, that's the only real color we can control with the multi-jets. And then FDM or FFF, depending on the printer you have, whether it's open source, the wonderful world of materials out there, there is almost anything that you could want, from wood-filled to metal-filled, copper to fiberglass reinforced to clear to glow-in-the-dark. Every hue under the rainbow is available out there. And so colors is relatively irrelevant to us out here. And we simply say, okay, and we're going to come back, make sure our scale is good there. We can preview it, but all it's going to do is give me a very simple, very non-color orientated saying, hey, this is what I'm going to do. We only really need to pay attention to this, again, if we're tweaking any of those settings in there. So come up here and close that guy back out. And I'm simply going to say, okay, and I'm going to write this out to wherever I'm going to store this. Again, whether I'm going to write this out to my USB drive, to take it over to my flash stick, take it over my SD card, in some cases, take it over to my printer, or write out to my network drive and send it. I say cancel just because if not, the Inventor Send a 3D Print Service is going to pull up a web page where I can then send my STL file to get a quote for printing that on there. So hopefully if you had any questions, hopefully this gave you some good ideas, some good starting points, a little bit of clarity on how do I take my part that I machine for the real world or manufacture for the real world, and how do I get a successful print out of it. Kind of a quick overview, wall thickness, resolution of the nozzle, and overall surface contact to the print bed, and that leads into the heat transfer. That's what will cause the warping and whatnot in there, all the way down to how small of a detail can I get away with my printer. And that just depends on the technology and or the hardware specifics of your printer. So I'm going to throw this back to Barb and let her wrap up. And if you guys have any questions, feel free to reach out to us.
Okay. Thank you, Kevin. Appreciate it. And so I hope that all of you were able to obtain some information. So thank all of you. Have a great day, and we'll see you soon. Bye-bye.